morning. Welcome to my session on distributed transactions. My name is Štefanko. I work as software engineer at Red Hat. I'm a big MicroProfile fan and enthusiast, and I'm also MicroProfile committer since August this year. And you can find me on Twitter under handle Štefank. I'm actually quite impressed how many people are interested still in distributed transactions nowadays. So let me start with a quick guessing game. Can you guess how many transactions, how many Bitcoin transactions there are per day? Wow. That would be nice. It's actually around 300,000 transactions, and this is significantly less than the normal bank performs per day. But you came here today to hear about something different, and that something different is called Saga. Basically, Saga is an alternative way how we can execute transactions. But before we dive into really how the Saga works, it's good to start with why we need it nowadays in microservices architecture. And for that, it's better to compare it with the traditional ACID transactions that you are mostly familiar with. So for my examples today, I will be using a simple transaction when we are going somewhere on a business trip. So we need to book 3 things. We need to book seat in a flight, we need to book a hotel room, and we need a car. So ACID transactions. Let's just quickly recap what ACID stands for. Atomicity is basically this all or nothing property that we expect from a transaction. That basically means that either all operations in a transaction are performed or none of them is happening. Consistency is, on the other hand, that the transactions will always leave the state of the system in a consistent way. So it means that if we start the transaction in a consistent system, then we must leave it after the end of the transactions, either successful or unsuccessful, again in a consistent system. Isolation stands for basically that if we have several transactions that are being executed in parallel, they cannot influence each other. That means that if we have 2 transactions, then the second one must appear to the first one as if it wasn't even started or as if already finished. We cannot see intermediate states of the operation. And durability just said that if we finish transactions either successfully or successfully, the result needs to be persisted somewhere in some durable storage. So how the transactions are being done today is basically on some form of consensus algorithm, and this is theoretical problem where we have a group of participating nodes or participants that needs to reach a shared decision. In our transactions case is basically a decision whether or not to commit the transaction. There are several protocols available right now, but the only one that is really being put into production and in use is two-phase commit protocol. However, there are some tries how to execute even these other ones, and if you are interested, there are a lot of papers on these particular algorithms that are really interesting, but they still share the same problem which I'm going to describe on the 2PC because it's the simplest one. So if we put this transaction into 2PC transaction, how it's being executed? Well, typically there is a process, or when we are in a distributed system, a standalone service or microservice, which is acting as a 2PC coordinator. This service typically receives the transactions, then it calls the individual operations on other services. I will talk directly about distributed systems, so this will be network, basically calls. The individual services will find the resources that they need to perform their operation on, then they will log these resources. They will not perform any operations, that will just like put it on the side, and then they will respond in the first phase back to the coordinator that they are prepared to actually execute their operations. In the second phase, if everyone in the first phase responded with a successful outcome, basically coordinator goes ahead and in second phase tell everybody, go ahead and perform the action that you need to perform. So basically commit. Then the logs are removed and the resources are actually taken, so the money are paid and etc. Then they will just send their confirmation back to the coordinator, and coordinator can say back to caller that the transaction was successful. In the second case, when some of the resources are unable to actually take the logs or perform the operation on the resources that are requested, then the coordinator must reach a decision to abort the transaction, and instead of commit, it will send an abort messages to individual services. Logs are removed, and the services are basically put back to the pool or return, rollbacked. Again, the confirmation is received, and we are sending back to the caller that the transaction was unsuccessful, And in this case, it can be retried later, or there can be some heuristic that can kick in. So what's the issue with this is that when we are doing this kind of scenario in a distributed system, we must expect that all of these components in this graph can fail. And this is particularly the case when after the first phase, everybody will take the logs, respond back to the coordinator that the resources are prepared, and the coordinator for some reason fails, or the calls are not delivered. In this sense, these logs are still being taken until the coordinator comes back up. And that means that if we have more requests coming for these resources and more, these requests are just blocked. And you are basically not getting any response, and your services are stuck until the coordinator comes back up. And why is this important is basically because we should strive to build reactive systems, basically, which are defined in Reactive Manifesto, if you are interested in reading more, which focus mostly on one attribute of the system, and that's responsiveness. Because really, if you want the long answer, it's written in a Reactive Manifesto. If you want the short answer, what do users do if you don't provide them with a response? And this basically leads eventually to the denial of service. So, and here is where the Saga comes in. Because all of these consensus protocols are to some way blocking because they really need to share this decision, Saga is saying that we will take the operations in the transaction and we will just go one at a time and we will actually perform it. That means that if we receive a request for a flight, we will not take any logs, we will actually pay the money and we will book the seat. Surely you can see that we are directly breaking acid because we are getting into inconsistent state, because we are holding flight and we don't have still car and hotel. How Saga deals with this fact is with something which is called the compensating actions, and we will get to it in a second. If you think that this idea of the Saga pattern is something new that we just discovered this year or last year, it actually was first published in a paper in 1987, and now we are just reinventing the wheel again. Basically, Mr. Garcia Molina and Salem described it as a long-lived transactions in a database environment where you basically don't want to take logs on tables for days or weeks. So, these compensating actions. Every operations that is part of the Saga needs to define a semantical undo action that will basically semantically revert the originally performed operation. This can be directly something similar as we have in 2PC, so it's like really opposite operation on the original performed operation. So if you are inserting a row in a table, then the compensation is basically just delete this row. However, these operations can be something that will actually change the state of the world. So you are working on a normal day and you will send an email as a part of the Saga. You cannot undo sending an email, but semantical undo means that you can send, for instance, another email which will just cancel the action that was originally requested in the original email. So you are back into basically same consistent state as before. However, you are in a state where there are 2 additional emails sent. So you are not rollbacked, you are semantically consistent. If you are interested about hearing more about this whole pattern and how it can be applied, there is a really nice presentation on YouTube by Caitie McCaffrey, where she described how they applied Saga pattern in a Halo video game, actually to collect statistics after matches. And it turns out that this kind of operation performance or execution is often sufficient enough for you to actually build your transactions. Because if not, then you can still go back to 2PC or other ACID, full ACID transactions. But if you don't really care about that you are slightly for some periods in inconsistent states, which is usually okay because imagine that you are ordering something. If you click order, you will get back nice screen, yes, your order will be processed. And if you get back in like 15 minutes an email that, sorry, we couldn't find something, you will just say whatever, and you will try again. So let's try to look now back to the same example, how we would execute it now in a Saga. There are several ways how to execute Saga, but the simplest one is when we directly have a Saga definition somewhere and we can send it directly to the individual services that are going to perform the operations. So we will, the client will send the Saga directly to the airline service. Airline service sees that it needs to book a flight, And it doesn't take any logs or anything. It will actually pay the money, and you actually now hold the flight. You have a seat reserved, and you are in an inconsistent state. Then it reads from the Saga definition, or it knows from some different place that it needs to call the hotel service. Again, the same action will be performed. You actually pay the money for the hotel, and you pass the Saga definition again somewhere else. And if you are able in this way to actually perform all the operations in a sequence as was requested, then the overall Saga was basically successful and you can return success. Where it gets interesting is when something is going to go wrong. And basically, if we now book the flight, pay the money, book the hotel, pay the money, and then we are trying to book a car, but the car, for instance, there are no more car left, so you cannot actually pay the money. So now you are actually in a state where you cannot go in a tree, but you already paid a lot of money for some different services. So Saga will deal with it in a reverse manner. So it will call the compensating actions on the services in a reverse order that actually allows you to depend in operations on the previous operations that were performed. And basically, it will just send cancel Saga message back to the service which was it called from. And the hotel service sees that it now needs to perform its compensation action, so it will just basically compensate. And this would mean that it will basically just reimburse back the hotel room. And again, it sees that it needs to pass the cancel Saga message back to the flight, and something similar can happen in a flight. Or for instance, the compensation action can be that they will try to rebook you on some later flight or something else. This is solely up to the individual services, what the compensations is. And the Saga as a whole is a concept which doesn't really care what the compensation is. It just guarantees you that either all of the operations in a sequence are going to be called, and in that sense, the Saga is successful, or if something went wrong, compensation actions are going to be called or all performed operations. So you are again back into semantically consistent state. Yeah, sure. Basically, you don't really see what the compensation action is, so we can only rely on a participant that will tell us what the result of the compensation is. And we will get into it later in our implementation. If we don't get a successful response from the compensation, we will going to retry again. So again, we will just return back the unsuccessful response, and the Saga can be retried later, or some heuristic can kick in. As this can be quite hard to follow when you are seeing it for the first time, I will repeat it with the individual operations that are going to be performed. So first, airline service will receive the Saga, and it will perform the operation book flight, pay the money for the flight, and book the ticket. Then it will send the message back to the hotel service. Again, operation that is going to be performed is pay the money for the hotel room. Now we are going to send the message back to the car rental service, and the car rental service is unable to book a car. Then it initiates Saga cancellation, and it will send back to the hotel service a message, Saga cancelled. Then the compensation action is going to kick in, so basically cancel hotel, and the same will happen for the flight. We will just execute the cancel flight. And again, these operations are defined by the individual participants, so we don't really know or care what these operations are. You as a participants are responsible for actually make sure that you will put the state back into, or put the system back into consistent state. And you will return it back to the caller. As you probably can guess, we are directly breaking acid with this, so we are no longer in a traditional sense a transaction. And what we are breaking is isolation, because if we have multiple Sagas executing in parallel, then different Sagas can see that the flight is already paid for, but still hotel and car is not. And we are breaking consistency, because this also introducing consistent states. However, what Saga utilizes is a different transactional model, which is called base. And if you are familiar with chemistry, you can see that transactions researchers are also very keen on chemistry. And this basically stands for basically available. That means that we are valuing with the Saga more availability instead of consistency. And this is back to the CAP theorem, where, if you are not familiar with it, it just says that when you are in a network, you cannot avoid failures, so you need to choose between being consistent and being available. Acid choose to be consistent, while Saga is choosing to be available, and thus you have responsive services. Soft state, this is exactly that we can see in a system these intermediate states of the Saga execution and eventual consistency. That means that even if we are not consistent all the time, the Saga guarantees that in some point in the future, you will eventually get into consistent state. Either all operations are going to be performed or all compensations are going to be called back in a reverse order. So there are two ways how to implement this in a distributed architecture, and these two ways are basically decentralization. This is what I was showing you so far, where the Saga is being passed between individual services. And the second one is something similar to ACID, that we have an orchestrator or the Saga coordinator in a system, which is a separate service that can either receive the Saga and then call individual services, or the Saga can be again passed between individual services, but each service is responsible to enlist with the Saga coordinator for the possible compensations. So if we are passing the Saga between services and we are enlisting with the coordinator, in case there is a failure, the coordinator knows which or what to call on individual services to perform the compensations. And with that, I will get into what we are doing in the MicroProfile. And this is basically an initiative that started last year, and we are currently in a RC1 phase with the GA planning by the end of this year. And it's called long-running actions. Basically, it's a translation of the Saga pattern into a Java microservices environment through annotations. If you want to see more, because this is where I start with the demo, it's available whole on GitHub, and basically this is, anything in Eclipse, basically an open source project. So if you are interested in this, or you would like to learn more, or even contribute, don't be afraid that it's called specification. Basically, it's a project as any else. If you want to contribute, just open it and please contribute. So I will show you now really quickly what this project is really about. So I have it open here in IDE. There are 3 modules, but the only important for us as a user is basically an API. There is also a specification document and TCK. But as you can see, the whole specification is a bunch of annotations R2 enums. And we will go through these annotations in a while, but as you can see, it's really simple from a usage point of perspective, because you are not dealing with these complexities on the background. This is up to the implementation. And currently, we have 2 implementations. One is provided in Narayana Transaction Manager by Red Hat, and the second one is in Payara server. But we are expecting more in the future. So, and with that, I will finally move to demo, and we still have half an hour. That's nice. So basically, I'm going to create a project from scratch, and I will use Quarkus for that. Quarkus is a new runtime introduced this year by Red Hat. It's basically running on GraalVM, and it's really fast. This is still not published. I did this only last week for this presentation, but soon it will be integrated into Quarkus codebase. In the end, there is a link for a demo which is using a different runtime, which is called Turntail. But for a demo purposes, please deal with me if something won't work, but it should. I tried it last week. So now yeah. Why not? Yeah, I can start with a new project. Yeah, I did it last night. So basically, this will just call the Maven Quarkus plugin, which will create a simple empty project, and we can go into this. And unfortunately, my idea expired like before this presentation, so I was installing it like 10 minutes before I started. So sorry for this. I need to like really put things together again. Where did I put it? Yeah, I want it here. Put things together, and I hope that everything will work, because then it will be unfortunate. So what this will generate for us is a simple project where we have only one JAX-RS resource, and basically we can directly with Quarkus run it. Sorry, first we need to add LRA as an extension, and then with Quarkus, if you want to add some functionality. It's similar to Spring Boot. You need to like include the individual features that you are going to use in your service, and then you will get uberjar or fetjar, which you can run from command line. But in Spring Boot, it's called starters. Here we call it extensions. And why not? Extensions. No, come on. Extensions. Yeah. So as you can see, there is a lot of them, and we have here a one which I edit, but it's still not in Quarkus itself, which is called Narayana LRA. So we can edit with Quarkus extension, and just to save typing, because I can see that I am really bad with it. This is a way how you can include a new extension in Quarkus. So this will actually include the MicroProfile array implementation and also the Narayana MicroProfile array specification and Narayana implementation. What I can do with Quarkus now is basically just compile the project and call Quarkus dev, which will run a live reload mode. And I will run it on port 8081 because Narayana is actually implementing the specification with that orchestration pattern. So I need to run in the background, Quarkus coordinator, which will run on port 8080. That's why I run that one on 8081. And while this is starting, we can just show that this is actually running now, and it is 8081/ping. Yeah, and we are getting hello message from, from this resource. Yeah, that's nice. Enable auto import would be nice. Come on, you can do this. And basically also LRA coordinator is basically another JAX-RS service, so we can also call it directly through command line. If you're not familiar with HTTP, if I'm just writing a port, it's basically only defaulting to localhost. So if I call LRA coordinator, it will basically returns from the coordinator all the LRAs that the coordinator currently knows of. Since we haven't started any, there is an empty JSON. And let me actually put this into watch mode, so we can see the LRAs that are being executed right away when we are executing them. And let me do a little, come on. This is i3, by the way, if you are not familiar with it. So this is all the windows that I have open. Yeah, and we can now type HTTP. So since we started Quarkus in a live reload mode, I don't need anything, any recompiling, anything. It will just work, as I will show you in a minute. So let's start with creating LRA resource, which will be a JAX-RS resource. Come on. Path. Yes. On LRA, and let's also make it application scope. Scoped. Because I lost my cache. That's nice. So, and let's just create an operation which will actually work as our original operation that we are going to execute as in Saga. So this would be public response core perform. And here we will just log nicely that we are performing an operation, and we will perform the operation, and then we will return response OK built. Just let me just create something that will basically just print something to see out. We don't need anything fancy for the demo. And here, no, come on. Cout p and just see out at the end. And perform operation for now will be only thread sleep, just so we can see it with 1 second interval on the coordinator. So we have our normal resource, which you are probably having now when you are performing some operation, and we want to put it into an LRA. To start with LRA or to actually execute this operation in LRA, all we need to do is put @LRA annotation on it. And this will basically now, if I go into right terminal and execute this endpoint, sorry, I make it bigger, 8081 array perform, this will actually go ahead, perform the operations, and if you were able to see it in the top right corner, you will see that the new array is started, and when the method finished, by default it is ended. However, this is just going to start it in the transaction, and basically we are not doing anything else. To actually enlist this resource as a participant in the transaction, we need to define this compensation action, because otherwise we cannot do anything with this resource in case of failures. To define a compensation action, we need to have a method which is annotated with @compensate. Pretty straightforward. There are two ways how to define this method. One is with Jaxares resources. This is particularly useful if you already have this kind of functionality. So if you have some eShop which has a resource, order something and then cancel order, you can just put this @LRA @compensate annotation and it will directly work. But if you are in a state where you don't really want to expose this operation to the outside world, you can also omit Jaxares annotation and it will still work. But for the demonstration purposes, I will stick with the default, which is Jaxares. So this really doesn't matter what the URL or the URI for your services are, because the coordinator is going to parse it when you are enlisting a resource into Saga. And basically, then when the possible compensation comes, it knows what it needs to call. And this will be, again, response compensate. And we will log nicely here compensate. And we will just return response, OK, built. So if I now run it, nothing else will happen because we are actually closing the Saga successfully. But if we want to compensate the Saga, we need to actually fail some of the operation. And to do that, there are two parameters in LRA annotation, which are cancel on and cancel on family. And basically, cancel on is just an array of HTTP response code on which, if they are returned from this method, the LRA is instead cancelled. And cancel on family is just easier when you need to specify a whole families of response code. Cancel on family defaults on 400s and 500s, so we don't need to actually include it here for now. But if you need to play with it a little more, you can. So all I need to do to actually cancel the LRA is to return 400 or 500 from here. So I will just return 500, and now if I replay this scenario, after 2 seconds, we see that the compensation action was called for the only resource that was enlisted in the Saga. And I didn't stop my work stuff. So we already now have what I was describing on the slides. We have a resource that is performing an operation as business action, and in case it fails, which is indicated with a status code, then the compensation action was called. Even in the case when the LRA is closed successfully, so we have this 200 return here, the LRA will also provide a callback, which is optional, and it's called onComplete. And where this can be useful is basically when you have when you need to remember something in your service in order to compensate. So for instance, if you have this order example, which I was talking about previously, then you need to probably remember at least the order ID in case the compensation is called, so you can associate that this particular order needs to be cancelled. And this complete method will allow you to actually tell your service that the LRA ended successfully, so you don't need to remember this anymore, so you can clean up. So if I just finish, this has pretty much the same semantics as compensate method, but it's optional. If you want to have a complete method, you also need to have it compensate, because otherwise this resource won't get enlisted as a participant. So I can do here response complete and log nicely complete and return response OK. So now we are again closing the LRA successfully. So in that case, when I now replay the same LRA, the compensation, the competition will be called instead of compensation. And as you can see, I typed the whole LRA service without stopping Quarkus once. So this is why I wanted to for a demo. And if you haven't tried it yet, please give it a try, because I don't need to actually stop this service for the whole session. And in the end, I can just compile it to the native and run it in a production if I want. So I was talking about actually associating something with the LRA, but since this compensation is called, you need to know which LRA is being compensated in case this resource is part of the several sagas at parallel. And this can be done by HTTP headers, or when you are not using HTTP, by the parameters which are injected. And for that, we need to inject an LRA HTTP context header, which stands for a long-running action. And this is basically just an URI, which represents this particular LRA. By default, when you annotate with LRA, there are several transaction types, which we will get in a while. The default one is required. That means that if you just use default LRA annotation, a new LRA is started when you are invoking this method, and in this by default ended when this method is finished. So to get this ID of this newly started LRA, we can just inject it as a header param, and in that sense we can log it here just to see that we are getting it. And let's also return it back, because maybe we will need it later. And this long-running action header you can also inject in any of these participant methods in complete and compensate. So if we are now completing still, I can do also header param LRA HTTP context header here. And in that sense, I should get the same LRA ID now when I invoke this service. So we see that it's for ending with 4D, and we are compensating the same action. So then you can have, for instance, some mapping in your service which will say that for this 4D, I am associating order 1. And if compensation for LRA 4D is called, I know that I need to cancel order 1. There are also several other headers which you can inject in these methods. The only important one right now is this recovery header, which is basically a subscription ID. It's again an URI, but it's more granular. So that while long-running action header, that context header allows you to enlist the same resource with multiple LRAs. This will allow you to enlist the same resource multiple times with the same LRA. So this is like subscription ID to a particular LRA. We don't really need to go into details, but you are also able to start transactions or sagas in a nested mode. That means that you are able to basically have multiple hierarchies of LRA executions. And if some lower hierarchy is completed successfully, it can still be later compensated. Where this can be useful, imagine the same business trip example, but let's say that you first want to book an economy class flight. And if this is not possible, then you need to book business class. So you can nest this as a separate LRA inside that whole business action. Let's just keep here HTTP context header. And with that, I basically covered the basics. There are also, what I haven't showed you right now is how to actually pass this LRA to a different service, because still we are only one microservice and we would like to the microservice architecture. So let me open a new terminal here and just copy this into a separate service. LRA service 2, open it in newly installed IDEA. Open as an existing project, whatever. And just maven compile Quarkus dev, but this time we want to run it on 8082. And we are good to go. So this is our LRA service 2, which now looks pretty much the same because I just copied it. And we would like to enlist this resource in the transactions which is started in LRA service 1. Now is a good time to talk about this values that are available in LRA attribute. As I said, LRA type required is the default one, which, if you are familiar with JTA, this is like one-on-one mapping plus the nested case. Required will start the new transactions if there is no transaction received when you are invoking this particular LRA resource. For what we are going, they are really nicely documented both in Javadoc and in a specification. So if you are interested, there is a lot of information on what these particular cases do. What we are going to use for LRA service 2 is basically LRA type mandatory, which means that if you are invoking this method, you need to receive a transactional or Saga context. And if you don't, the call will fail with precondition failed, I think. So let's use LRA type mandatory, and let's go back to LRA service, and we know that the LRA is active only in this method because it is ended when this method is finished. So before we are going to perform our operation, let's just really do a client builder. Let's just do an invocation to LRA service 2 to actually enlist also LRA service 2 in this transaction. So we will do target, and this will be localhost 8082, and again LRA perform, and we will do request get, and this is everything that you actually need to do. Actually, how the context is transformed from one service to another is again by this LRA HTTP context header. However, the specification says that if you are performing any outgoing JAX-RS calls from a method which is executed inside of the Saga context or LRA context, this header is automatically appended to your request, so we don't need to do anything else. We can, for instance, if you are really running multiple transactions simultaneously, you can choose which one you want to propagate, but since we are running only one, the default will be sufficient for us. And with that, if I haven't forgotten anything, if I now again invoke LRA service 1, which is in top left corner, we should receive a perform call also in LRA service 2, and we can see that the completion actions were called on both services. So we are already having a distributed transaction, which is running on my local host for now, but these are HTTP calls, so it doesn't really matter. In the future, we plan to include in a specification itself support for different protocols, so you can exchange HTTP for Kafka messages or JMS. But for now, with 1.0, since this is one of the more complicated MicroProfile specifications, we are sticking with HTTP. So if we go back into the specification, we can see that LRA and one other annotations are under VS RS package. That means that you need to put them on JAX-RS resources. The other ones are not, so they can be used without JAX-RS. But you need to follow some semantics which are defined by the specification. So we get a really nice info message here, which is basically saying that when we were trying to finish the transaction in LRA service 1, we were unable to do so because it was not existing anymore. And this is because by default, the LRA which is received in any JAX-RS method is ended when this method ends. So that means that we started a new transaction in LRA service 1, then we propagated it to LRA service 2, which passed because we received it as a header, automatically added on service 1. And then when this method ended, it completed the transaction when this method ended. To get around it, there is a parameter in LRA annotation which is called basically end, which defaults to true. So if we say here false, that means that basically just don't end LRA when it's here. Then you as a users are responsible to close this LRA because the system will not track it or like keep the track of LRAs which are still being active. So if I now try to repeat this, we should get just rid of that info message. And as you can see, both services are automatically reloaded, so I don't really need to do anything, and we get rid of the complete message. However, even if you have end false, if you, for instance, cannot perform this operation in LRA service 2, so we again can return here 500, for instance, then compensation, of course, will get precedence over the end false, and if we repeat this call, we see that the compensations has been called. And again, we are unable to close it in service 1 because it was closed in service 2. Let's just put this back. And with that, I will like to show you one more thing, and that's another annotation which is part of the specification, which is called after LRA. You can pass basically LRA through services without actually requiring them to enlist within the transaction. So for instance, if you have a chain where you need to only enlist first and a third service, the second one can still pass the LRA ID back to the third service, but it doesn't necessarily need to enlist it. And this is defined with this compensate annotation. So if that middle service doesn't have compensate, it will just pass the ID to whatever outgoing JAX-RS calls it's going to make. However, every service is allowed to declare an after LRA method, which is again required to be a put JAX-RS resource, or basically this one doesn't. And let's just call it after. And this method is called after any LRA that passed through the service without the need to actually enlist is ended. And it will give you the end state of the LRA. So if we just do here after, we can inject again the LRA HTTP context header. So, oh, sorry. No, now we actually need to inject LRA HTTP ended context header because what this functionality can be used for is basically when some LRA ends, you might want to start a new LRA. And this is exactly what you would use it for. This is why the LRA HTTP context header is reserved for the newly started LRA, which will possibly start when this method is invoked. So we can here use URI ended LRA, and we also get in a response an LRA status, which is enum of values, which are basically the states the LRA can be in. And we can log nicely here after, and let's just do LRA ended LRA and also its status. And return response, okay, built. So if we now replay the LRA, when it's finished, we see that we had an after LRA method invoked and the state of the LRA is closed. With that, I will move back to the slides for a while. What I showed you so far is basically 3 states that the LRA can be in. It's active for the duration of the method, while basically you don't request close or cancel. And after you request close or cancel, it will go ahead, try to call all the completion actions, and then it transforms to the close state. Or if something went wrong, it will call all the compensations in reverse order, and it will transfer to cancel state. However, there are more states, and basically you can also say from this complete or compensate method that you are unable to perform this operation. So you can return another enum, which is called participant status of these values. If you say from complete or compensate that you are unable to do this action, so fail to cancel or fail to complete, basically the LRA as an algorithm is stuck. We cannot do anything now. We can just log this message somewhere and some manual interaction from administrator is needed or some heuristic needs to kick in. There are 2 more states, which are basically intermediate states in between closing and canceling. These are states in which we are actually calling complete or compensate methods. However, you are also allowed to return from complete or compensate participant status immediate state. That means compensating or cancel or closing. And in that sense, you will get this method called again. I would show it you if we have time. I don't think so now, but it's actually a part in the tutorial which will be linked in the end. So basically, if you return closing or canceling the same, let's say we will stick with compensations now. If you return compensating from the compensation method, then after some timeout is elapsed, the coordinator will call this method again. And if you again return compensating, it will call it again and again and again. That basically means that it's forcing you to write this method as idempotent, which is restriction that you need to enforce in your business actions. If you don't want to do this, or you want to reuse, for instance, some resources that you already have, there is an option in a specification in which you can define a method which is annotated with status, and this would look really similar to the compensation, which will be called instead. So if the first time we are going to invoke compensation, and the compensation will return compensating, then in the next step we are going to invoke status method if it is present in our array resource. The only annotation that there are two left, that I didn't mention is forget, which is basically a method similar to a complete, but for these failure cases. Unless you are able to really return end status, that means completed or failed to complete, or compensating, failed to compensate, then we are going to retry to call them again and again. That was the question that was asked. This forget method is used that in case this compensating status will end in a failure, the forget method will be called also, so you can perform that cleanup action that you will be originally performing in complete annotated method. The only one left is called leave, and this is basically if you are invoking it with an LRA ID or LRA recovery ID on a resource which is enlisted with some LRA or this particular recovery or that subscription ID, it will basically unsubscribe it for it if the LRA hasn't entered one of the closing phases yet. And this is all that it is in LRA specification. And basically this is enough to put together a really strong transactional framework which can work. One last thing that I would like to show you before we close this is not ending this LRA anywhere. That basically means that I will put end false even here. That means that we are creating a new LRA in LRA service 2. We are not ending it LRA service 2, and we are now not ending it now even in LRA service 1. So to end it, we need to have another LRA annotated method. You can have as many as you want in one service, so you can reuse compensations and competitions or any other callbacks to that extent. Here we can again use that type mandatory because we want to call it with active LRA, and just to be precise, even if it's not necessary, we want to close this method, and this will be again get, and let's call this end, and it doesn't really matter what we are doing here. Public response end, and here we will just log ending, return a response which will actually be interpreted to LRA in which mode it should be ended. So we want to close it successfully, so let's just call it here OK. And we will need LRA ID because we are going to execute it in mandatory context. So if it's not going to be executed with LRA ID, we will get back 412. And that's 412 LRA ID. And let's just say that we are ending this LRA ID, and I'm missing semicolon. And come on. Yeah. So if I'm not now going to replay the scenario, we see that the actions has been performed, but there are no completion messages or that after LRA annotations. We are just in a state where the LRA was performed, and we can see that LRA coordinator knows that it is still in a status active. So now you have a control over when the LRA is ended. So unless I will call HTTP 8081/LRA/end, and yeah, I didn't. This is what will happen. I try to invoke mandatory LRA, but there is no transaction. So we need to actually, copy the LRA ID, and we will pass it as a long-running action header here. And in this sense, the competition callbacks are invoked after LRA method is invoked, and LRA is ended successfully. And I have 20 seconds left, so If you want to use it, basically what the Quarkus extension does is including this MicroProfile array API dependency, which is now an RC1. And if you want to use Narayana LRA is your way to go. And if you like what you are doing, please go on GitHub, MicroProfile array, spread the word that there is another transactional solution. If you don't like what you are seeing, please go on GitHub and click issues or pull requests and fix it. And that would be everything from my side. Thank you for your attention.